My name is Ilse Vonk. I am a senior graphics programmer at Nixxes software. And for the past 3 years, I've been responsible for designing, maintaining, and developing our custom memory manager, NXMem12. My goal of this explanation is to explain how we handle our memory management and what systems we have in place to optimize our memory usage. I'd like to begin by sharing the core design philosophy that has guided the development of NXMem12. The core design philosophy that I followed was to keep things simple, which for the memory manager came in 3 different forms. First of all, keep things simple for the players. At Nixxes, one of our other core design philosophies is that the game should look and behave the same as long as the same settings are used, no matter what hardware you have. So this means that if you use the very high texture quality setting, no matter if you use a 3 GB GPU or a 12 GB GPU, the same large texture quality budget will be used. If you have no system in place to handle this for you, this will result in terrible performance. This is because the operating system will demote what it deems necessary. Having to stick to both mine and Nixxes' core design philosophies, I decided against automatically adjusting budgets based on the amount of available video memory that we have. And I also decided against overwhelming the user by giving them key details about how we do the memory management, like by giving them access to our usage and our budgets. Instead, I chose a third approach. We can leverage the additional information that we have available to handle the demotion ourselves. We have more time and more resources available than the operating system does, so by taking control of this process, we can ensure that the game remains playable even if the player oversubscribes on video memory. Second of all, keep things simple for the users of the library. NXMem12 uses a mirror of the DirectX 12 allocation interface, which makes it incredibly easy to integrate. It also, of course, has some specialized methods which generally either hook into the same DirectX 12 allocation interface, or it is also allowed to make more informed decisions and use one of our other optimization methods instead. The only major deviation that we have from this pattern is the releasing of resources. NXMem12 allocations aren't reference counted, so they need to be explicitly destroyed. And lastly, keep things simple for the developers of the library. For NXMem12, I use compartmentalization to maintain simplicity. Instead of having one monolithic memory manager, NXMem12 is split up into several distinct systems which either work independently or in tandem with each other. This helps us to isolate and solve problems while keeping the code base clean. Since each system is largely self-contained, this makes it easy to optimize or fix bugs in individual systems, even for users of the library who haven't been using it that long. This is also because each interaction is clearly marked by a method call, ensuring that the communication is clear. This talk will be divided into multiple sections. First of all, I'd like to talk about our demotion system, what it is and how it came to be. Then, I'd like to highlight our dedicated resource allocators, how these are one of the ways that we improve our allocation speed as well as reducing our memory footprint. And I'd also like to highlight one of the key features that they have, which is defragmentation. Next up, I'd like to talk about the debugging interfaces that we have, what our essential tools are, how they work, why they're important, how they can be used, and of course, some practical examples. And lastly, I'd like to close the talk off with some tidbits, which are some smaller topics which I still think are worth mentioning, but they weren't big enough for their own section. One of the key features that distinguishes NXMem12 from other memory managers is that we handle the demotion ourselves. Whenever you start to run low on video memory, we make our own decisions about what resources should be moved to system memory, and vice versa. But what is demotion exactly? Demotion is done by the operating system. It does this whenever you start to run out of video memory. It will then automatically move resources in the background from video memory to system memory. It does this to ensure that there's enough memory free for both your application as well as other applications on the system. There are not many heuristics that we can use to control the demotion system from the operating system. And it also doesn't have a lot of time available, which makes it difficult for it to make smart decisions. The only way that we can influence this is by using residency priorities. These residency priorities are a hint to the operating system indicating how important a resource are, but they are not guaranteed to be demoted in that order. Once enough memory is free again in the video memory pool, it will also automatically start moving resources back from system memory to video memory. Each iteration of the demotion system had a couple of steps in common, which were classifying new allocations, collecting allocations suitable for demotion, creating demoted heaps and resources, and, of course, copying data from the original resources to the demoted ones and patching the allocations. To stay true to my philosophy, I started with a simple proof of concept. This simple proof of concept did all of these steps except the classification on sequence on the main thread. This prototype was incredibly functional, but the stutters whenever the system kicked in were kind of horrendous. It turns out that creating about a gigabyte's worth of memory takes a considerable amount of time. On certain systems, I've seen this take up to a second. So I started to speculate which of these parts could be offloaded to a separate thread or could be deferred to a later frame, and I came to the following conclusions. The collection must remain on the main thread. The resource creation could be completely offloaded to a worker thread and deferred over multiple frames. The patching, however, must remain on the main thread, but could be deferred to a later frame. So I made a new prototype, but the cracks quickly began to show. By the time that we got around to the actual demotion, certain allocations were no longer eligible for demotion, which resulted in memory corruption. Others were already deferred released, resulting in hard crashes, while others were certainly mapped, resulting in even more memory corruption. So I limited the creation that the worker thread had to only a single frame to work around the deferred release problem as well. And this iteration worked a lot better, but the stutters still persisted. Not as severe, but we couldn't work around them. So I went through iteration after iteration, and it became incredibly clear to me that this system could not be scaled any further. It was too integrated inside of the memory manager and its allocation that decoupling it completely from that seemed almost impossible. I struggled with this problem for quite a while. How do you take a system with so many edge cases that is completely centered around the memory manager and its allocations and make it run smoothly across multiple threads? So one day, while commuting home by train, I was pondering this very question. I glanced over at my ticket and I started to wonder, how do they function? After thinking about this for a while, I realized that I had the solution to my problem right in my very hands. Imagine that you have two factories, one in which they assemble cars, and one in which they manufacture car parts. Whenever the assembly factory has a broken car and needs a part replaced, it doesn't send the entire car over to the manufacturing factory. No, it creates a description of the part that it needs and sends that over instead. The manufacturing factory then starts to create this part, but meanwhile, the assembly factory creates new cars. Once it's done, it sends it back over, and the assembly factory uses it to fix the working car. In this analogy, the memory manager is the assembly factory, and the parts factory is the worker thread, and the communication happens through tickets. I realized that the main flaw that I had with my system was that it was way too focused on the allocations. This focus was not necessary. Instead of focusing on the allocations, it could be completely decoupled from the memory manager and its allocations by focusing on the underlying heaps and resources. Whenever we want to demote an allocation, only the underlying heaps and resources need to be replaced, which means that the only thing that we actually need are the descriptions for both. Once these new heaps and resources have been created, all we have to do is copy over the data and patch the allocations. Because of this, we only have to handle edge cases in three different moments. First of all, we got to check the viability when we want to schedule an allocation for demotion. Next up, we got to do the same whenever we want to do the actual demotion to ensure that the allocation is still viable. And lastly, every frame, of course, we need to handle the deferred release. So now with this, there's no dependency on time anymore. It could take an actual hour for demotion to complete. But as long as the allocation that is associated with the demotion is still around, the system will still work as intended. So now we finally made it to the design of the demotion system. It is a multi-threaded system which uses a ticket-based communication system to handle the communication between different threads. There are three different types of tickets that we can send back and forth. The first one is sent from the main thread to the worker thread and is used to request a new demoted heap and resource. For it, we need a heap description, a resource description, and a unique identifier of the allocation that requested it. The second type is sent back from the worker thread to the main thread whenever we have a demoted heap ready. This will contain a pointer to each, as well as that same unique identifier. The last type is sent by the main thread to the worker thread whenever we want to cancel an in-progress ticket. And this only needs to contain that unique identifier. The demotion system works in 5 key steps. The first thing that we have to do is classify which allocations are eligible for demotion. Then we got to collect the new tickets, so find out which resources should actually be demoted. We got to process the completed tickets. We got to fulfill the tickets on the worker thread, of course. And of course, we got to handle the communication between the main and the worker thread. 1. Classifying eligible allocations. Whenever an allocation wants to be created with a dedicated heap and a dedicated resource, we calculate a priority for it. We only calculate a priority for resources which are not CPU and GPU writable. So anything that is, for instance, a UAV or that is a render target gets excluded from this, as well as the ones that are CPU writable. For all of the valid ones, we calculate a priority. This priority we mainly base on size. We have 16 bits available for this priority, so we actually split it up into multiple buckets. Each bucket is about 10 kilobytes. We then use this priority to prioritize larger resources over smaller ones. But since we don't want to immediately move over a 2 gigabyte buffer if one is available, we actually have a threshold in place. The moment the size goes over that threshold, we start to reduce the priority again at the same rate in which it increased. By doing this, we ensure that we favor resources of around the size of the threshold. We also apply an arbitrary boost to buffers, since these tend to be sampled less frequently. Only resources with a valid priority are eligible for demotion. 2. Collecting new tickets. Well, the first thing that we got to do is figure out if we actually need to collect new tickets. To do this, we gather the budgets, adjust them based on in-flight operations, and then check against some thresholds that we have in place. Once we go over a certain threshold, we start to demote resources again until we get to a third defined threshold. And once we have less than a certain amount of video memory free, we have more than a certain amount of video memory free, we start to promote resources again. To decide which allocations should be demoted, we create a sorting priority for them. This sorting priority is 64 bits and contains multiple different parts, which I will go through from least important to most important. We start off with a couple of bits which are dedicated to the pointer of the allocation. We use this to filter out any sorting conflicts. Using these bits, we can ensure that the resources get promoted and demoted in the same order as they were promoted or demoted originally. Next up, we got the priority as we calculated earlier, followed up by a couple of bits dedicated to how often these allocations have been used over the last couple of frames. So with this, we ensure that resources which have been used recently get prioritized to stay in video memory over resources which haven't been used recently. And lastly, we get an elevator priority flag. Whenever this is set, that means that the allocation should remain in video memory for as long as possible, but it's not time critical for it to stay there. So it can be moved over if it's necessary. We then sort these allocations based on their priority. For demotion, we go from lowest priority to highest priority, while for promotion, we do the opposite. Then we loop over all of the allocations and check if they're viable. The viability check consists out of a couple different parts too. First of all, we got to ensure that the resource has not been created or accessed recently, since this most likely means that there are GPU operations related to them currently in flight. Next up, we got to make sure that, of course, it's not already marked for demotion, that it hasn't been recently mapped, and that it's not in a writable state. We also have a last special flag, which we can specify ourselves to indicate that an allocation is locked. We'll get more into how we use this a little bit later. For each eligible allocation, we can create a ticket and mark them for demotion. Once we have marked enough memory for demotion, we break out of this loop. 3, processing completed tickets. Let's assume that the worker thread has completed enough tickets and that the associated allocations still exist. The first thing that we have to do is loop over all of these allocations and ensure that they're still eligible in the same way as we described earlier. For the ones that aren't, we now release the resources associated with the tickets and remove the mark for demotion. From this point on, we ignore these. Then, of course, we got to ensure that the old resources are in a state that we can copy from. Then we copy over the data from the old resources to the new ones and queue the old ones up for deferred release. And then we get to the actual patching. The patching consists out of two different parts. The first part is patching the allocation itself, which means updating the internal ID312 resources, as well as some metadata that we keep around for these allocations. And the second part is a callback to the engine. The engine can register views which are associated with the allocation, and using this callback, we can ensure that the descriptors inside of those views get updated whenever we actually do a demotion or a promotion. Lastly, of course, we got to transfer the new resources into the state that the old resources were in before the demotion happened. We do this to ensure that we can do the demotion seamlessly. And of course, we can only do that if we have a valid synchronization point on both the CPU and the GPU timeline. 4, fulfilling tickets on the worker thread. What the worker thread does is actually fairly straightforward. It just takes a ticket, creates a heap, creates a resource, and sends back the result. The synchronization, however, is a little bit more complex, so I'd like to highlight that a little bit. The first thing that it does is wait indefinitely. It does this until a tickets to fulfill event has been set. This is set by the main thread whenever it has requested that new tickets should be fulfilled by the worker thread. When we do this, enter critical section so we can do the synchronization safely, and we start moving around some data. First of all, we take the newly requested tickets and put them into a local queue so that we can process them once we're out of this critical section again. Then we take the canceled tickets that the main thread has requested and remove them from both our internal processing queue as well as our completed tickets queue. And then we move our completed tickets into the shared completed tickets queue so that the main thread can once again take these and process them locally. Then we can simply leave the critical section and set the event if we have fulfilled any tickets. Then we get to the actual processing of the tickets, which is just as described earlier. There are two ways to break out of this loop. The first thing, of course, is if we run out of tickets. If we have no tickets left to fulfill, well, then we might as well wait indefinitely again. Otherwise, we also have a strict time budget that this worker thread needs to stick to. We do this since we need to ensure that the synchronization happens frequently, because otherwise, the queues that we have for requesting tickets as well as deferred release, they get pretty large. So by ensuring that we synchronize pretty often, we can keep those down. Whenever we break out of the loop, we also manually set the tickets to fulfill event if we still have any tickets left in our processing queue. After that, we return to the beginning and then either wait indefinitely for the main thread to set the event again, or automatically continue if we set this event ourselves. 5, managing the communication between the main thread and the worker thread. The first thing that happens is that the memory manager populates a list of new tickets to request, as described earlier. Then we got to check a couple of things. If we have requested any new tickets, or we have any outstanding tickets that should be canceled, or the tickets fulfilled event has been set, we now enter a critical section. Inside of here, we have to fill the canceled tickets queue with any resources that have recently been marked for deferred release that had any operations in progress. We move over our newly requested tickets, so the one that we populated earlier, over to the shared requested tickets queue so that the worker thread can access these later. And of course, we got to take the completed tickets so we can process them locally. We also have to take the canceled tickets queue that we just filled and remove any of them from our local completed tickets queue. This is because these requests have happened after the last synchronization point, so they could actually have been completed by the worker thread since that last synchronization. Then we can leave the critical section, and if we have requested any new tickets, set the tickets to fulfill event. Then we get to processing the tickets as described earlier. One of the main ways that we reduce both our memory footprint and allocation and reduce the time that it takes for an allocation to happen is what we call the dedicated resource allocators. Once again, I took my design philosophy into consideration here and came up with a solution which is both scalable as well as which is scalable. It consists out of two different parts. The first part is the dedicated resource allocator itself. The second part is an allocator which lives inside of the dedicated resource allocator. This allocator subdivides the backing data and is completely disassociated from any memory management itself. Once again, compartmentalization ensured that we had a simple implementation that was easily scalable. Whenever an allocation wants to be made inside of a dedicated resource allocator, we first have to check its viability. We do this against some information that we provided at creation time, which we'll get more into in a little bit. Assuming that this passes, we then loop over all of the different backing data associated with this dedicated resource allocator and check if this allocation can be made in any of them. If it does, great. We simply create the allocation, move on with our lives. Otherwise, we have to create a new backing data and allocate the new allocation inside of it. There are two different types of backing data that we support. The first type is the heap backing data. For the heap backing data, each allocation will simply contain a resource inside of that heap. While for the second type, the resource backing data, each allocation will take that resource and has an offset into it. The only resource type that we currently support is the buffer type. For the backing data type of heap, the size of the heap indicates the size of the backing data, while for the resource backing data type, the width of the resource indicates the size of the backing data. There's quite a bit of information that is required next to this whenever a dedicated resource allocator gets created. We need to know what allocation type this dedicated resource allocator should be registered for. We also can specify a maximum resource size that an allocation is allowed to be inside of it. This is separate from the size of the backing data, so we could have a really large backing data while only allowing small resources to be created inside of it. And lastly, we got a multitude of different flags that we can specify, most of which have to do with how the memory should be reclaimed, while some have to do with alignment restrictions or if defragmentation should be used. For the heap backing data, we also have the heap description. The size here is indicated by the heap size. And for the resources, we need parts of the heap description, as well as, of course, a resource description. There are three different types of backing allocators that we support. The first one is the most trivial of them all, which is a fixed block allocator. It only allows you to allocate fixed-size blocks. It's incredibly fast because of that, and we used it in the past for readback buffers, which are very small and of a fixed size. Second of all, we got a snake pool allocator, which you can think of as an extension upon the fixed block allocator, since what it does is it allows you to allocate multiple blocks in a row. It's still incredibly fast because of this, and we still use this to this day to allocate ray tracing buffers. Since for ray tracing buffers, there's a very strict alignment requirement that we need to hold, which makes it a perfect use case for this allocator type. And lastly, we got the free list allocator, which is the most complex. It can allocate blocks of any size and will decide for you automatically where the allocation should be located and try to reduce waste as much as possible. This makes it moderately fast, but you can use it for literally anything, and we do. Since we use it for so many different things, performance actually becomes quite important. So we started out with a simple implementation, but this turned out to but we needed to optimize this a bit. So the first optimization that we made was that we started to use a header pool instead of allocating backing data for each header individually. So with a header pool, you simply allocate a big block of memory and then subdivide it for each header, which really increased our cache coherency. Next up, we started sorting our free list, not to increase the allocation speed, but to reduce the amount of waste that we were seeing, as well as to reduce the amount of unusable blocks that we had. This sorting quickly became a bottleneck, however, so that's why we're now using a bucketed approach of this, where each free list allocator has up to 16 different buckets, where which header is allocated in which bucket is dependent on the size of the header. Each of these buckets is sorted from smallest to largest. If this was all that the dedicated resource allocators were able to do, it wouldn't be that interesting. Luckily, they can also be defragmented. Defragmentation is used heavily for small textures, specifically the ones which use the 4K alignment size. Modern texture streamers create a lot of small MIPs in a short amount of time and then immediately stream in higher versions of those MIPs, which might not all fit inside of this dedicated resource allocators. Due to how deferred release works, this can sometimes happen faster than the allocation process can actually happen faster than the release process is happening, which resulting in a lot of small gaps. This problem only gets worse and worse over time. I've gone through many iterations with the defragmentation system as well, but since it's a less complex system, I won't go through the history and jump straight into the solution. Once again, my philosophy of keeping things simple was my starting point. Defragmentation, it comes in many different forms. I decided to go for a simpler approach of defragmentation, which might not be the most optimal, but gets us at least 90% of the way there. The main reason why I chose this approach is since it does not require us to create new heaps. We can only defragment to already existing heaps. So keeping things simple here also came in another form, which is by ensuring that the entire implementation can happen on a single thread. To do this, the entire system is split up into small, bite-sized chunks, which can either be completed completely or partially every frame. There are many different stages associated with the defragmentation, which are selecting a backing data to defragment away, gathering the allocations from said backing data, creating new allocations inside of other backing data, copying over the data, and of course, patching the allocations. And lastly, we of course got to clean up. I will now run through each stage and explain if and when they can be deferred. First of all, selecting a backing data to defragment away. We select the most empty backing data. But we then also take the indices pointing to all of the other backing data and source them based on how full they are, ensuring that the most full backing data are first. Then, of course, we do a sanity check to ensure that there's enough free memory inside of all of the other backing data so that we're not defragmenting while we don't have enough memory available. From this stage, we always immediately flow over into the next stage, which is gathering the allocations. Now that we have in backing data, we need to gather all the allocations from that backing data, and then we also have to gather the metadata associated with the allocations inside of those backing data. We store this locally so that we can safely process this. We then, of course, have to ensure that they're viable for defragmentation. This check is similar to the demotion check that we did earlier. This is the first costly stage, so it generally flows over into the next stage, but sometimes it gets deferred. 3, creating new allocations in the different backing data. First thing that we have to do is sort all the allocations based on their size, from largest to smallest. Then we loop over all of these allocations, and for each allocation, go over all of the backing data in the order that we sorted to earlier. We then check for each of those backing data if this allocation could be fit in those, and we do this until we find a spot for them. We keep doing this until either we run out of allocations to find new places for, or we run out of time. The defragmentation system is very time-boxed to ensure that it's not taking up too much of your CPU time, so this can actually be split over multiple frames. If at any point we run out of our time budget, we simply store wherever we were and then keep going from there at the next frame. 4, copying over the data. What this is exactly depends on the underlying resource type. In the case of heaps, we create new place resources, transition the old resources into a copy source state, copy over the data, and then transition the new resources into the states that the original resources were in, very similar to how the demotion system handles it. For the resources, however, we follow the same steps, but now it needs to be done on the backing data level instead of the individual resource level, since all allocations share the same underlying resources. So we transition the backing data and copy over the data as before. This stage always flows over into the next stage, since from this moment on, the new resources should be used. Which is why we now get over to the patching. The patching step is identical to the patching step of the demotion system, except that we now also got to take the metadata that is stored inside of the allocators into account. We then, of course, delete the old resources so that we can free the now empty backing data. Next up, we got 6, cleanup. The cleanup step always happens after the patching step. And what it does is it cleans up any state that was used for the defragmentation, as well as resets some internal timers that we have to ensure that the defragmentation can happen again. If at any point any stage fails, then we go back to the cleanup step as a backup. Any tool is only as strong as its debugging interfaces, which is why I've dedicated quite a bit of time on developing strong debugging interfaces for NX 12. Each system inside of NX 12 has their own debugging interfaces, which can be enabled or disabled at runtime. Some of these systems require some additional command line arguments to function properly, since they require more CPU time or RAM. I started off with simple ASCII interfaces. I did this because it was very easy to implement, since I could just reuse some already existing infrastructure inside of the engine I was working on at the time. This allowed me to focus on developing the library, while still being able to convey all the information that I had to. As NX 12 grew, however, it became more and more difficult to maintain all of these textual interfaces, especially the graphs. So I started to look at what other tools were available inside of the engine I was working on at the time. And I once again spent quite some time on refining these debugging interfaces, and I was able to develop more concise and organized versions of these interfaces. Once I transitioned to yet another engine, I applied what I had learned to create an engine-agnostic interface. It uses a simple draw rectangle and a draw text callback to ensure that it's versatile and adaptable to multiple engines. Because of this, we no longer need to update the debugging interfaces inside of the engine itself whenever we make any changes to how they work. Since if the new version of the memory manager is there, these will already be built in. Not to worry, however, the original ASCII implementation still lives on in the console, at least partially. I hope that I've now shown you that even the simplest tools can effectively convey the same information as more fancy ones can. And I will now go through the different debug interfaces that I think are important and explain what they show, how they can be tweaked, and how they are used. Let's start off with the most important one, which is the memory statistics. These will tell you exactly where the memory is located. There's only one setting which can be changed, which comes in 3 different stages. And we use this to control how much information the system should convey. The first stage doesn't give us any information about the game's actual memory usage, but it instead tells us how much memory is taken up by D312, D312MA as if it's enabled, and it will tell us how much memory is unaccounted for by NX 12. Memory that's unaccounted for by NX 12 is generally memory that's allocated by other libraries. We use this to know if we're staying within our budgets, as well to know if we have any memory leaks. Memory leaks here come in 2 key forms. The first one is when the amount of unaccounted for memory stays the same, in which case we know that we're not releasing an NX 12 resource. If the amount of unaccounted for memory keeps rising, we're not releasing an ID3012 resource reference. The second stage gives us more detail about the game's memory usage, but only on a higher level. It does this in the form of allocation categories, which is grouping multiple allocation types together. Each category has a couple of key metrics that it shows. It shows us how many allocations are inside of this category, what the size is of all of these allocations together, and most importantly, how much waste those allocations have. Waste here is a very interesting concept, especially during the early stages of development. It allows us to easily identify where we can reduce the memory footprint. Let's take buffers for an example. If we want to create a 12-byte buffer, then description is just going to contain 12 bytes. Then we make the actual allocation, but if we check the description again, the size is actually going to be a lot larger. So if we compare this new description against the old description, we know how much wasted memory there actually is. And this difference in size is what we call waste. We use this to narrow down where our memory leaks are coming from, where we should focus our optimizations, for instance, by reducing memory targets for texture memory or things like that, and of course, where we can reduce the waste by using dedicated resource allocators. The third stage is the most detailed of the 3. It tells us the exact allocation types. This will tell us exactly where the memory is located. While the previous menu gave us a high-level overview and allowed us to trace it to a specific allocation category, this will allow us to trace the waste down to an exact allocation type. One thing that is interesting that I would like to highlight here is that we mark unused entries with a darker gray. This makes it much easier to know where the memory is actually located. Previous versions of this debugging interface did not have this, which resulted in a lot of wasted time looking for valid entries. Next up, the demotion system. The demotion system can be tweaked in a multiple of different ways, but there's two I would like to highlight. First of all, the stress test. Whenever this is enabled, it will continuously move memory to and from system memory as fast as it can. We use this to know if the demotion system is working properly and if it's hooked up properly inside of the engine. If it isn't, this will generally show in the form of memory corruption. And second of all, we have a debug video memory budget. We can use this to emulate either specific systems or specific lower-end cards, so that we can emulate how the demotion system would behave on those video cards. The main debug interface associated with the demotion system is the memory graphs, which come in two forms. We have the video memory graph and a system memory graph. I'd like to start off by highlighting the gray marks that we have on both bars. Starting off with the rightmost one on the video memory graph. The moment that the bar, so in this case the yellow part, surpasses that mark, we start to demote video memory. We do this until we get to the middle of the two marks on the video memory bar. The one in front of that, the moment that the bar drops below that, we start promoting memory again if it's available. We do this once again until the middle of these two bars. The one on system memory is also very important, however. The moment that the amount of system memory that we're using goes over that mark, then we need to disable the demotion system. Since if this is the case, we're completely out of system memory. And completely running out of system memory generally results in more hard crashes than completely running out of video memory does. This gives us a general overview of exactly how we can interact with the memory. Each color here actually indicates how we can interact with it. So I'd like to go over those, starting off with blue. Blue is memory that is not registered for the demotion system. This means that this memory is always locked in place. Red means that it is registered, but it's currently immovable. It has been locked. Memory that is locked generally are textures which currently have a MIPS operation in progress. Whenever a new MIP gets streamed in, with how modern texture streamer works, there's a bunch of operations that are fairly difficult to keep track of. So these MIPs, we just lock the resources associated with them to ensure that they can't be demoted at this time. Next up, we got the yellow section. The yellow memory means that it's registered for demotion, and it can also be demoted at the time. So this is the main amount of memory that can be moved over from video to system memory, as well as back. Then we got magenta, which is used to indicate what memory currently has an operation for promotion or demotion queued up. And lastly, we got cyan, which is used by the reuse system, which we'll get more into a little bit later. We use this to know how much over budget we can actually go, so when the demotion system can no longer do what it needs to. And of course, also to know if the demotion system is working as intended. This video shows the demotion system in action, and what you can see is that the moment that the yellow surpasses the ladder mark, it starts to demote to system memory, while the moment that it drops below the first mark again, the memory goes from system memory to video memory again. We also have a textual version of this interface, which shows us exact numbers. It also shows us how many active commands that we have in progress related to the memory manager. We use this to know if the stutters are coming from the memory manager or are unrelated from it. We can use this to determine our actual demotion statistics. So for instance, if we need to figure out what our minimum spec should be, we can use these numbers to know the exact minimum memory that we need, of course, with a little bit of a bias to ensure that our programs can also do what they have to. Next up, we got the windows associated with the dedicated resource allocators, of which there are two. The first one just shows us some general information about the individual dedicated resource allocators, how much memory they're taking up, how much of it is actually in use, and how many backing data they have. There are no settings to tweak this menu, it's just a simple overview. Next up, we got the defragmentation, however. The defragmentation can be tweaked in a couple of different ways. We can disable the defragmentation system in its entirety. We can enable stress tests similar to the one of the demotion system. And we can limit how much time the defragmentation system is allowed to take up every frame. So this is the debug menu associated with the demotion system. It gives us a detailed breakdown of exactly where the memory is located. We use this to know if enabling defragmentation would help us. So in the case of the top window, it would actually help us since there's a lot of green space, and green means that it's not currently used. Well, in the case of the bottom graph, well, it's mostly red, so there's not much that can be defragmented too. This gives us a visual indication of how much memory we're actually using, since each line indicates a backing data. In this video, you can see the demotion system in action. So the moment that it kicks in, a lot of the partially used backing data start to disappear. The last one I would like to highlight is the call stack tracking system. At one day, I just simply hooked up the call stack gathering system that we had for things like asserts to the memory manager, and it turned out to actually be incredibly powerful. It now tells us exactly how much memory and how many allocations we have per individual call stacks. This system itself cannot be tweaked, but what it shows can. We can change how it's sorted, we can tweak how many lines per call stack are displayed, and we can specify how many call stacks we want to skip, and we can filter it in a multitude of different ways. We, for instance, can use this to locate where we're currently having a lot of waste, as well as where our memory leaks are coming from. By using the memory overview, we can track down to an individual allocation type and a memory location, and then we can filter down in this window to find out exactly what the problematic call stacks are. I'd like to end this part off by giving some practical examples of these debugging tools in action. The first one happened a little while ago and has to do with a memory leak. QA reported that a crash was happening when ray tracing was enabled when you died a whole bunch of times in the same spot. So I loaded up the game, enabled the small versions of the memory statistics, and died in the same place over and over again. It became fairly clear to me that the system was not working as intended because the amount of unaccounted for memory, the D312 memory usage just kept climbing. The amount of unaccounted for memory, however, stayed the same, which indicated to me that an NXM12 resource was not being destroyed. So I went up to the large memory, and enabled the large memory statistics, and noticed that the ray tracing buffers just kept climbing. We were getting more and more of them. So I put this into the call stack tracking, filtered down to the ray tracing buffers, and I was able to find out the exact problematic call stack. After this, it was fairly trivial to find out where we were missing the release. The second one happened a little bit more recently and has to do with the demotion graphs not working as intended. I was traversing the world when I noticed that the demotion system was about to kick in. But when it did, only about 30% of what should have been demoted actually got demoted. I turned around and another 30% got demoted. So I loaded into a couple of different levels and noticed the exact same behavior. So then what you do is just go to the settings and start tweaking them and see which one have any effect on this. And I noticed that the texture quality had an effect on this. The higher the texture quality was, the less memory got demoted. So this indicated to me that the texture streaming code was not behaving as intended. I checked it out, and I noticed that streamed-in textures were always marked as writable the moment that the MIP streaming was done. This actually resulted in the opposite behavior that we wanted. Resources which were in view were demotable, while resources that were never used for rendering were not demotable. So I added the missing transitions, and the demotion system worked as intended again. I'd like to close this talk off by addressing some smaller topics which I still think are important, starting off with the allocation types. I've been referencing these throughout the presentation, and this is an overview of all of the different allocation types that we support. The ones that are black are the ones that we can automatically detect, while the ones that are gray need to be specified by the user. The user, however, can specify any type that it wants, so it doesn't necessarily have to match what we would automatically detect. Next up, we got a create resource method, which is basically a big wrapper for memory allocations. It will decide for you how an allocation should be made. It can also do the automatic classification that I mentioned earlier. It will use a dedicated resource allocator if there's one registered that is valid for it. It can use D312MA if the resource is small enough to basically ensure that we're packing the small resources as well. And it can decide to create a dedicated heap and resource for an individual allocation so that it can be classified for the motion. Next up, we got a create alias method. This has been specifically designed for dynamic resolution scaling. One common way in which dynamic resolution scaling is implemented is that one heap is created for the largest resolution of a specific render target. Each smaller resource is then aliased inside of that same heap. On certain hardware, however, smaller resolutions can actually require a larger heap. This method has been designed to detect this and automatically create the larger heaps and recreate the new aliased resources inside of this heap. I've also been mentioning D312MA throughout this talk. D312MA stands for D312 Memory Allocator and is an open source library that is developed by AMD. Originally, this was a catch-all for all small resources to ensure that they were still being packed properly. As NX112 developed, however, it became possible for NX112 to handle these resources itself. So in older titles were using D312MA as a fallback for these small resources, while more modern titles decide to handle this themselves. The reuse system, well, originally we had no need for this, so it's actually not in our older titles. But due to the increased bandwidth with the texture streamers, we actually started to notice microstutters. And these were related to the create heap calls that we do whenever we want to create a resource that can be demoted. Originally, we only had about a couple of these every frame, while now with the modern texture streamers, we can easily see a couple of dozen every frame. So this system has been designed to temporarily hold on to demotable released heaps, and these then will be used first. It will only hold on to these heaps temporarily for either an X amount of seconds or until we run out of memory. If we start to run out of memory, the system has been designed to automatically disable and empty itself out again so that it doesn't interfere with the demotion system. That is also why its size is on the same graph as the demotion system so that we can see if we actually start to interfere with the demotion system. There are also a few more improvements that I would like to make if I had the time. First of all, I would like to expand the demotion system to be able to demote defragmentable resource allocators. This is because we already know that we can move these resources around, so why not simply move them over to a demoted heap, right? And second of all, the reuse system. It is a band-aid on the fast texture streaming problem. So what I would like to do instead is expand the demotion system to be able to handle multiple resources inside of single heaps. If we could demote these, well, then we could start creating these. But this could also be a little bit tricky due to resources having variable sizes, so it might be difficult to pack them together in a single heap. So this is still a work in progress idea that we're working on. I'd like to leave you with the following words. I hope that I've shown that even high-quality tools can come from humble beginnings. As long as you keep iterating, and most importantly, keep things simple. Are there any questions?
Can you turn me on? Yeah. Go. Questions? I'm trying to work from front to back with the questions so that I'm not running both ways.
Hey, thanks for the talk. Were you able to prevent Windows doing the demotion for you?
No, we cannot prevent Windows doing the promotion for us. There's no way for us to influence that, which is why we set up our thresholds in such a way that we always handle the motion ourselves before the operating system kicks in. Generally, we can do that, but sometimes we do get into a situation where a lot still needs to be demoted. For instance, because of the user starting up a new application, in which case the operating system can actually decide to demote something for you, which is why we also still specify resource priorities. We specify the priorities that the operating system use on all demotable heaps, to ensure that if the operating system decides to demote something for you, it will still demote the least important things.
Got it. Thanks.
Okay.
Hi. So my question is, how does this system work when there's other applications that also use like a lot of video memory? Like how do you handle the budgets? And how do you ensure that you're not getting any video memory?
So the way that we handle the budgets is we actually take the lowest size that has been reported over the last couple of seconds, and we use that as our budget until we run out of the time budget again. So we do that to ensure that we don't constantly keep fluctuating the budget that we have, and that we try to knock into a situation where we think that we have more memory available than we actually have. And then let's say we are using 6 gigabytes and we only have 4 gigabytes suddenly available. Then we start to demote everything that we can until we get back either down past that 4 gigabyte range or everything that we can demote has been demoted to system memory. Okay. So it's a little bit of a reactive approach compared to preventative approach.
So if there's another application, it can basically take your memory because you will demote. So that often happens with applications like Chrome, with videos running in the background. Whenever this happens, they can suddenly take up a lot of video memory, so then we just react to that to ensure that we have enough video memory free, that nothing of ours get demoted. Okay, thank you.
Do you actually do anything to detect if resources have been demoted by the operating system, or is it just purely based on the budget?
Yeah, we don't detect ourselves if a resource has been demoted by the operating system. As far as I know, there's no easy way to do this, so we just completely base it on the budget that we have. Hoping that in the case that the operating system has demoted something, that we freed up enough video memory again that it will promote it again.
You mentioned defragmentation, but I didn't really get when you do this. Do you do this every now and then, every frame, whenever it works out?
Yeah, so we use a time budget for this. So every couple of, I think a half a second or so, I think we generally use as an approach here. We check if defragmentation should happen, in which case we do the first step where we select the backing data to defragment away, and then check if it fits within the budgets of the other backing data that we have. If it does, then we do the defragmentation itself. Otherwise, we go into the cleanup step, which resets that budget again. So half a second later, we can check again if if defragmentation should happen.
Okay.
There's one more in the back.
Okay, I'm getting there.
So the important part is, how do you do the sorting? What do you find out? What to demote? Because if you go bindless, how do you know what is needed or not needed? That's a high-level game decision. So you need to tweak this for every game differently?
Yeah, so this is actually different for every game, but generally either during a gathering step or during an actual bind SRV or bind UAV step, depending on how modern the engine is. We then mark these resources as used. In certain games, we cannot use this approach due to it fully being bindless. But for this, we still have certain steps in place, like, for instance, the texture streamer, which we can use to handle these mark as used calls instead. So then we only mark resources as used once every frame to just indicate that they have been used recently. But we don't have any actual statistics about, this is how many times it's been bound or used for rendering or things like that.
Okay, yeah. So if it's on that, then if it's on SRV or whatever level, then you don't know what MIPS it needs, or it's not MIP driven then. So
Sorry,
then
could you repeat that question?
Then you hook into the high-level texture streaming system, which was already there in the game.
Yeah, we hook into whatever is already there, and we just we just add the statistics wherever we can.
Okay.
Okay, I think that was the last question. Thank you very much.